today we will continue on with neural networks. Okay, so just so there's no confusion, neural networks are not covered in our textbook. Okay, and this is I'm just kind of going off of other resources that you can find online. In particular, I'm using the Welch Labs series on neural network, those videos on neural networks, so I'm kind of using that, and then we'll use these notes as kind of inputs here. And so right now the neural network that we have, we've got 2 input nodes, 3 nodes in our hidden layer, and then 1 in our output layer. And so from our input node, we've got x1 and x2, and they feed into the 3 nodes in our hidden layer, and then we apply a function to at each node in the hidden layer, and they come out and go into the output layer. We apply a function at the output layer, right? So our inputs appear in our X matrix, and we have our first weight matrix, which we call W1, okay? And we multiply those together, and we get our Z matrix at our second layer, okay? So we've got X times W1. Then we apply a function to our Z, and we'll call this our A matrix. For whatever reason, I think in the Welch Labs video, the A matrix is lowercase, so I'm just going to follow the same convention there. We take the outputs from the A2 weight matrix, and we multiply this by our second weight matrix. And this becomes Z at the third layer, and then finally we apply our function to Z, and this becomes our predictions Y. Okay, so our predictions here. Perhaps maybe I'll go through and I'll just apply some dimensions here. So I've got n by 2. W is going to be 2 by 3. Z is n by 3. A is going to be n by 3. We have n by 3. W is 3 by 1. And Z will be n by 1. And then thus Y hat is n by 1. And what we want to do is we want to train our network. And what we mean by training our network is we want to use the training data to find the best set of weights W, okay? So that means training data to find the best set of weights in matrices W1 and W2 that minimize our loss function. Okay, so far so good. I think we covered this on Friday, and I'm hoping at least this is kind of familiar. Just refreshing the setup of the network. Okay, and to train our network, in order to find the W's that work best, we're going to use gradient descent. okay? And the idea with gradient descent is that you take basically the derivative of the function, we call this the gradient, and instead of trying to set it equal to 0 and solving, we're just going to say the gradient tells us which way is uphill and which way is downhill, and we're just going to start at some arbitrary spot and just keep taking steps downhill. And that will get us to the bottom of the hill, rather than taking a direct solve, set it equal to 0 and solve. So this is what we're doing. We're doing gradient descent. Okay, so, and that means basically just take steps downhill. Downhill. Okay, and downhill is a small step in the direction opposite of the gradient. Okay, so the way this is going to work is that the values in W at time n plus 1 will be our current values in W at time n minus some small value lambda times the gradient of F at our current values of W. So that's what we're going to do. The function, okay, our loss function, F is our loss function, which is basically the sum of the residual squared, which is y minus y hat quantity squared. And in order to help us, or just make things a little bit easier, we're just going to artificially insert the scalar of 1/2, okay? This changes the value of the loss function, but it doesn't change the value of where the minimum is, right? Just multiplying the whole thing by a constant is not going to change the location of the minimum, so it's fine. Okay. Just so you know, in the video, in the Welch Labs video, he calls this function J. Loss function is called J. So when he's talking about J and whatnot, this is the loss function. Okay, and what we want to do is just keep in mind we have two weight matrices. We have two weight matrices, so we're going to have to figure out the gradient for each one. Okay. Okay. So W1, our first weight matrix, W1 is, the dimensions are what? Are 2 by 3. And so when we take the gradient, what are the dimensions of the gradient going to be? Also 2 by 3, right? Because all we're going to do, the way gradient descent is we just take this matrix and then we add on the result of the gradient matrix, right? So this also has to be, also must be basically 2 by 3. So over here we've got 2 by 3. The gradient is also going to be 2 by 3. Okay, and then the second weight matrix, W2, is 3 by 1. So the gradient with respect to W2 must also be 3 by 1. And so keeping that in mind will help us kind of navigate the math, which does get a tiny bit hairy, but I'll walk you through it, and I hope we survive okay. All right, we ready? All right, great. All right, so first we're gonna we'll first find. So basically, we're gonna work backwards a little bit, and so we will first find the loss function with respect to W2, the gradient. Sorry, we will find with respect to W2, okay, which we said is 3 by 1, okay. Okay, so all we're going to do is we're going to just say gradient of L with respect to W2 is going to be ddW2 of the sum of our loss function, y minus y hat squared, okay? I'm playing a little fast and loose with the math here. I mean, everything is correct and works out, but I'm not going to get hung up too much on certain parts here, okay? And because it's you know, the derivative of sum is the sum of the derivatives, we will do this, okay? And so you can think of this, first we'll just worry about individual values, okay? And then we'll worry about the sum later, okay? So we'll deal with the sum a little bit later. Okay. So just a few notes. So y is our data, and y does not vary when W2 changes, okay? So that will be helpful, okay? However, y hat are our predictions, and they depend on what values we have in W2. Okay, so let's just kind of take a look. ddW2 of 1/2 times y minus y hat, okay? So when you take the derivative of this part, the square comes down, right? And then you have to apply chain rule, and so you would multiply by -1 because the y hat is affected, dy hat of dW2. So the derivative becomes this, okay, and so this becomes -1 times y minus y hat of dy hat dW2. Okay, and what I'm going to do is we're going to say, well, okay, well, how does y hat change with respect to W2? Okay, so I'm going to just write recall that what y hat is equal to f applied to Z3. Okay. And our function f is the sigmoid. F of z is equal to 1 over 1 plus e to the -z. Okay. So what we'll want to do is we'll want to find we'll have to find the derivative of this thing, okay? So what we're going to do is, well, you say, okay, well, y hat is equal to this. So I'm going to just kind of split this out, and I will just say y minus y hat, and then we will kind of just split this to dy hat with respect to z3, and then dz3 with respect to w2. Okay? And then how does y hat change with respect to dz3? This changes, this is going to be equal to f prime of z, and f prime of z will equal e to the negative z divided by 1 plus e to the negative z squared. Okay, how did I get that? That's just a quotient rule. If you just this quotient rule, the derivative of this is going to be of u over v is u prime v minus v. uv prime over v squared, right? So that's what we have. So you treat u as 1 and v as this. U prime v minus uv prime divided by v squared. Quotient. So anyway, this is f prime of z, and this is this part right there. Did I mess something up? No. Okay. Okay, and then so let's get kind of put everything together. We got minus y hat times f prime of z. So I'm just going to do f prime of z here, just to kind of, so I don't have to rewrite this whole thing. I'm sorry, f prime of z3. And then we've got d z3 with respect to d w2. Is this okay so far? Okay, and then so on the next slide we'll take care of dz3 dw2. Okay, so far what we have is we're at negative y minus y prime times f prime of z3 times dz3 with respect to dw2. Okay, how does z3 vary with respect to the second weight matrix? Okay, so keep in mind, you know, we're in our network. If the outputs here are z3, and z3 is equal to basically the outputs of our second weight matrix, A2, times W2. Okay. And so how does Z3 change with respect to W2? Well, it just, this part is basically just, it's just A2 multiplied by W2. So it's just our A2 matrix. So okay, and then does A2 vary with respect to W2? It does not, okay? A2 is everything that happens before we multiply by W2, so it does not change with respect to W2, so we don't have to worry about dA2 with respect to W2, or I mean, you could throw that in there, but it doesn't. It's unaffected. Okay, so this is where we are. Okay, now if we take a look at the dimensions of this, you know, we have a few things going on here. Okay, so y, if we think of the vector, all right. So if we think of the vector y is n by 1. The vector y hat is n by 1. So these two together are n by 1. Okay. The vector z3 is also n by 1. Okay. So how can we multiply something that's n by 1 by n by 1? Well, we have to do element-wise multiplication. Let me just bring this down to here. This is going to be n by 1. Okay, and so the multiplication here, we have to do element-wise multiplication. Okay, so these two things will remain n by 1. Okay, and the A2 matrix is an n by 3 matrix. Okay, and so to kind of take care of this, what we're going to do is we're going to bring A2 to the front and transpose it. Okay, and so what we will do is we bring it to the front and transpose. And so we will get A2 transpose, which is now going to be, well, I'll do the dimensions at the end. I got A2 transpose times minus y hat times f prime of z3. Okay, and so the dimensions on this is 3 by n multiplied by, and then all of this, because we kept it as element-wise multiplication, is n by 1, and thus the result is 3 by 1. Okay, so this is our loss, the gradient of the loss function with respect to W2, and this is going to be 3 by 1, which is what we want. So we have A2 transpose, and what we will do is we'll define just this quantity, delta 3, as negative y minus y hat f prime of z3. Okay, and so here I've got, 3 by n times n by 1, and this is delta 3. Okay, so this is our gradient with respect to W2. Are we okay so far? Okay. Okay, and then, so this is a 3 by 1 matrix, right? 3 by 1 matrix, this is exactly what we want. Okay, now we've got to find the gradient of the loss function with respect to W1, okay? And so we can start off kind of following all the same steps, because we ask how do these things vary with respect to W2, or now we ask how do these things vary with respect to W1, okay? And so because W1 affects what A2 are, pretty much all of these things hold true, okay? So now we're going to find the gradient of the loss function with respect to W1, okay? And we can just say the same steps as dW2 until we get to this step, okay? So we get to minus y hat times f prime of z3, and now we want to know how does Z3 change with respect to W1. Okay. And earlier we defined this quantity as delta 3. Okay. Okay. And so this is going to become, I'm going to just say delta 3 times, now we say, okay, well, Z3 varies with respect to A2, and A2 varies with respect to W1. Okay, so if we just keep in mind A2 is equal to the f of Z2, which means that we will have to split out A2 and dW1. So here we've got delta 3 times Z as it changes with respect to A2, and then A2 changes with respect to Z2, and Z2 changes with respect to W1. Okay, earlier we said that Z3, how does Z3 change with respect to A2? So again, if I draw the kind of the network here, the weight matrices here are W1, and then the weight matrices over here are W2. So the A2s come out over here, and they feed into Z3. So the way Z3 changes with respect to A2 is that it is just multiplied by the W2 matrix. Okay, so this just becomes the W2 matrix. So here I've got delta 3 with respect, and then we're multiplying this by the W2 matrix. The W2 matrix is 3 by 1, whereas delta 3 is n by 1. So in order for it to fit, we're going to transpose this so we have a 1 by 3. How does A2 change with respect to Z2? Well, dA2 with respect to dZ2 is just going to be f prime of Z2. So this part becomes f prime of our Z2 matrix. And then lastly, we want dZ2 as it changes with respect to W1. Okay. So f prime of Z2 is going to be n by 3. Okay. So these multiply together to form an n by 3, and then these two we will do element-wise multiplication. So we have n by 3 and n by 3. And then we have dZ2 with respect to dW1. Okay, so how does Z change with respect to W1? Okay. Well, if we say, well, what is Z2? Z2 we said is equal to our X matrix times our W1 matrix. So Z, the way it varies with respect to W1 is just X. So we left off here, we said delta 3 times W2 transpose times F prime of Z2 times D Z2 with respect to D W1. Okay, so this thing is just X. Okay, and earlier we said we have a n by 1 and a 1 by 3. These combine to n by 3, and over here I've got n by 3, and we're going to have element-wise multiplication. X is n by 2. So how do we get all of this to kind of fit together? We're going to bring x to the front and transpose it. So we're going to have x transpose, which will be 2 by n now. And then I've got all of this, delta 3 times W2 transpose F prime of Z2. And again, these combine to n by 3, and we've got element-wise multiplication here. And so here I've got basically a 2 by n times an n by 3. And this leaves me at the end with delta L with respect to W1. And this is going to be a 2 by 3. 2 by 3. So just kind of, I guess I'm rewriting this. And that's our 2 by 3 matrix for our gradient of W1. Did that work? Lecture slides. Okay, so those are the gradients that we have of the loss function with respect to W1 and W2. Okay, so and the dimensions line up because W2 is a 3 by 1 and W1 is a 2 by 3, and our gradients end up being 3 by 1 and 2 by 3 as well. Okay, and so it was a little bit tough, but we figured out the math. Okay, and so now all we have to do is we just code this up in R so that we can apply gradient descent. Okay, so there we go. Okay, and so I've done this for you. It's it appears in CCLE, and let me just change my how I do this console on the right. That's good. Okay. Okay, so what we have, is that good? Here, I can probably squeeze extra. Okay, so I'm going to put in our data x, and then we'll put in our data y. Okay, so we got our input data, our output data, and then I will, what's often helpful is to kind of put everything on a scale from 0 to 1. Okay, it's because the sigmoid function, its output is on the range 0 to 1. So all I'm going to do is just divide by kind of the column maximums and divide y by 100 so that they're on the scale from 0 to 1. And then when I build my neural network, I'm going to put in variables. Just say input layer size is 2, output layer size is 1, and hidden layer size is 3. And this just makes it easier so that later on, if I wanted to change the size of my hidden layer or input or output layers, I can do that without having to worry too much, okay? And now I'm going to create my first weight matrix, W1. And all I'm saying is it's just going to start off with as a matrix of ones, where the number of rows is the input layer and the hidden number of columns is the hidden layer. So it's going to be a 2 by 3 matrix here. Oops. Then I say Z2, so I'm just doing the forward feed part. Okay, we say, okay, I've got my X, I've got my first weight matrices. All I'm going to do is multiply X times W, and that's going to form Z2. Now I define the sigmoid function, which is 1 over 1 plus e to the negative z. And in the video, the Welch Labs video, he creates a plot. Okay, so that's the only reason why I include this line, but it's not necessary for the thing, okay? And so the A2 matrix is just going to be applying the sigmoid function to the elements in Z2. So we just do this, okay? So far, if I look at A underscore 2, what are the dimensions of this? It's going to be n by 3, right? So in this case, it's 3 by 3. I've got 3 input values in X, so it's n by 3, okay? Our second weight matrix is just W2, and it's 3 by 1. And I multiply the A matrix by this, so Z3 is going to be n by 1. Okay, and then we finally apply the sigmoid function once again to this, so that y hat is also n by 1. Okay, and then now the cost function is just going to be the difference between y, y and the y hat, but now I need my scaled values of y, which are in the matrix capital Y. Okay, so I've got capital Y and then y underscore hat. Okay, and we're going to take the difference between our the current estimates and the true values. Okay, and so our current estimates are terrible. And so it returns back and it says this is the cost that we have, 0.015. Okay, how are we going to do the gradient? Well, I'm going to create a function called sigmoid prime, which we did the math for earlier. It's e to the negative z divided by 1 plus e to the negative z quantity squared. Again, the Welch Labs video includes this plot, but it's not necessary. Okay, and so here all I'm doing is I'm just directly coding exactly what we found in the math part. We said we're going to define delta 3 to be, where did that slide go? We're going to define delta 3 as negative y minus y hat f prime of z3. Okay, and that's exactly what I wrote here, negative y minus y hat of f prime of z3 for delta 3. And then the gradient with respect to W2, I'm using the same as the video notation, J instead of L, the loss function. We said that is delta 3 times A transpose, okay? So I've got A transpose times delta 3. So I'm just putting exactly into code what I've done by math. And then if we go on over here, we said the result for the gradient of the loss function with respect to W1 is X transpose delta 3 times W2 transpose, where we do element-wise multiplication between delta 3 and W2 transpose times, I'm sorry, not element-wise here, element-wise between this times this and f prime of z3, okay? And so so that's what I have coded here. I've got delta 3 times W2 element-wise multiplication by sigmoid prime Z2. Oh, I guess I'm calling this quantity delta 2. So this quantity from delta 3 to the end, we're calling delta 2. And then this, the last thing will be X transpose delta 2. Okay, so I've got X transpose times everything above. And that's what we have, dj dw1 and dj dw2. Is that okay? Going from the math to the code. All right, this is kind of the hard part. And so now, when I check the gradient, what should the dimensions of dj dw1 be? The same as the dimensions of W1. So we want a 2 by 3 matrix. Okay, indeed, that's what we have, a 2 by 3 matrix. And then we want dj dw2 to be the same dimensions as W2, so we want a 3 by 1 matrix. Okay, and that's what we have. We have a 3 by 1 matrix. Okay, and then so the gradient descent part, I just pick a kind of an arbitrary scalar and I say kind of the next values that we're going to do will be, we're going to take our current values minus some scalar times the gradient. And we do this for W1, we do the same thing for W2. We take our current values minus some scalar times the gradient to just take a step downhill. And we do it for both sets of weights. And so we can see the current cost that we have right now before we update it. This is our cost, 0.015. And then we will do forward feed again. We're going to say X is, Z2 is X times W. Then we apply the sigmoid function to Z. We multiply the second weight matrix times that output. And then we apply the sigmoid function there. And these will be our new estimates after we took a small step downhill. Is that okay? And so we can kind of compare, you know, how did our old y-hats go? Our old y-hats look like this, and our new y-hats look like this. Are these better? Well, let's, excuse me. We'll calculate the cost function on these new values compared to these values. And we can see, okay, the original cost was this, and after we did some updates, our cost is lower. So that's a good thing, okay? And so that means we did indeed take a step downhill. And now we would repeat the process. We would say, okay, now I'm at a new location. Let's calculate the gradient again. Let's take a step downhill. And we would just repeat that over and over and over again. I'm going to skip over this part on numeric gradient checking. Okay, this is kind of a, whenever the math is hard, you should go back and see if you did your math correctly. There's a few ways to do this, and one, and we'll talk about this briefly, or we'll talk about this on Wednesday, is that one way to do it is just kind of say, well, what is the gradient? The gradient is, the derivative is really just how much did y change when I changed x by a tiny bit and so on. And so this is kind of a way to do that. I'm going to just skip over this for now, okay? And we'll go ahead and we will just do gradient descent to kind of get to the bottom of the hill here, okay? So I'm going to just start anew. Instead of having, I'm going to initialize my weight matrices, but instead of using the values 1 for all values of W, I'm going to just use random uniform values for W1 and random uniform values for W2. Okay? And then I'm going to create a vector called cost underscore history, length of 10,000. And basically, I'm going to just do gradient descent. So in each iteration, I start off and I just do the forward feed. I take our values X and our estimates of W1 and W2, we forward feed to get y hats, and we calculate the cost of y hat at this point, and I store that in my cost history matrix. At that location, using the W1 and W2s that I have, I calculate my gradients, dj dw2 and dj dw1. Then I do gradient descent by just taking a small step in the opposite direction of the gradient. I just update W1 by taking a small step, and I update W2 by taking a small step. And that's the entire thing for gradient descent. And then I just repeat. Once I update my W1 and W2 matrix, I go back to the top, I recalculate my estimates of y hat, I recalculate the gradients, and then I update my weight matrices again. And I just do this over and over. Each time I'm recording the current cost between y and y hat. Is the loop here okay? Does that make sense? All right, so all I'm going to do is just going to run that. And R says it's done, okay? And we can take a look at what our weight matrices look like. This is my weight matrix for W1, 2 by 3. This is my weight matrix for W2, 3 by 1. My estimates, y hat, if I plug in X and I do these things, these are my estimates for y hat, okay? 0.74998, 0.82005, and 0.92989. Okay, compare this to the true values of y of 0.75, 0.82, and 0.93. This seems to be pretty good, okay? And we can take a look at our cost, and we can look at how our cost changed as we took steps downhill. And so we can see in the beginning, we took the steps downhill were very steep, and then we reached a spot where, you know, we were taking steps downhill, but we weren't making that much progress. We found a little bit more, and now I guess we're still taking steps downhill, but they're very, very shallow steps downhill. Okay, so we seem to have done pretty okay. All right, we'll talk more about gradient descent, but here is kind of the first results of our first neural network that we've done.